It's unknown load. The reaction force or reaction moment, you treat it as a load, and then the structure becomes determinate. Then you solve it. Either use the equation or use superposition. Right? So last time we talked about using superposition, and actually this is the one example we went through, right? So today I want to just continue on the indeterminate beam, go over a few more examples. There was a comment based on my survey there. Remember, you guys fill out that sheet. So we just finally, Travis helped me collect all this comment there. So one comment was the examples we have in the class, maybe it'll be the easier or too easy compared to the homeworks. So homework seems to be hard. But I think if you want to try the easy ones, there are quite a few easy ones there. I just didn't assign. So you should try the easy one. You can try the easy one as addition, practice, and then do that one there. The reason I gave that, I'm not trying to intentionally make it really harder. I just feel that kind of the problem there is more representative, what we cover, what we need there. So if you can do the homework, I think the exam should be about the same level there. So I don't want to make the exam really, really hard and homework really, really easy. So that's not a good practice for me. So basically, I'll suggest you try a few other problems to warm up, then you do the homework. That's one way. Another one is we can actually incorporate a few more challenging problems in the class. So we're going to go over one that's definitely harder than homework today. Okay. So the first one, since we already finished this one, so the first one example I want to go over is just a little bit variation from this. So let's say we have a beam. Okay. Now on this side, if you have a spring, okay, so the load can be anything. Let's say you can have a distributed load, or you can have a constant force, right? And plus a distributed load. Say you want to make it more complicated, right? So I have two types of load here. You have a Q, that's known, right? Q, let's say equals 5 or 10, and P is also known, right? So let's say you want to give a number, let's say 20, Q equals to 5, right? So we know the length of the beam. Let's give equal to 10. Just randomly give a number, okay? So now there is a spring here. So we know this spring has a constant K. So the value is known. Okay. So now the question is, under this load, right, how much this point going to deform? What's the delta? Let's call this point B, right? So what's the delta B? This point A. When you have this beam under these two loads, one the constant force and one is distributed load. But there is a spring support there. So I want to find out how much this point is going to move, or how much force you're going to have in the spring. Okay. So is this determinate or indeterminate? Indeterminate. Why is it indeterminate? Because you're going to have, this is if you remove the spring, it's a cantilever beam. Now you add the spring, so you have a redundant or additional restriction. So that makes it indeterminate. That's a quick way. Another way is you can write the equation of equilibrium, right? You're going to have RA here, RB here, and then you have a MA there. So 3 unknowns, but you have only 2 equations. So it's indeterminate. All right. So quickly we can say, okay, it's indeterminate. That's for sure. Right? Okay. Now, how can we solve this problem? Find out the delta B or the force in the spring. Superposition, easier, right? Then you solve the equations. Okay, superposition. How can we use superposition here? You identify the redundant restriction, right? How about we say the spring, you add the spring there. So the logical one selection is use the spring. So if you take away the spring, then your beam will be like this. Okay, so spring, you replace it with a reaction, what we call it, RB. That's the R or spring, right? Okay, then you're going to have a load, constant force, P here, and you also have a distributed load Q. Should RB be down or up? Can be either way. I don't know yet. Right? So you can assume anyway. But my feeling is it will be up because you're going to press on the spring. Right? See, without the spring, this point is going to move down. Now the spring will prevent it, some resistance there. So therefore, the spring must push it up. That's my judgment. It can be wrong. Then you find out finally what's the result there. Okay. For example, you have a load P and the Q. One is up, one is down. Then you don't know their balance will push the beam up or down. Then it can be anyway. But anyway, you have to assume one direction. Then you can write the equation and find it. Okay. Let's say based on our sense, maybe most likely it can be going upward. So we'll just assume it's up. All right. Okay. Now for this beam, can we use superposition find the solution? Yes, we can divide this up into 3 situations. One is a beam with a concentric force P. Another is a beam with a distributed load Q. Then another one is a beam, cantilever beam with a concentric force RB. So basically you have 3 loads there. Right? For each one, okay, now we don't have to solve it. We can just go to the textbook. End of textbook, you have the appendix there. Right? Remember we used this last time. Yes? Okay, reaction at point A. Do we need to take that out? I mean, label it, find it for now? We don't have to. You can try to find it. Write the equation of equilibrium, draw the free body diagram of the beam. But you don't have to. Why? Because once you reduce the stress, remember we always say remove the redundant restriction. That's the RB. Once you remove it, now it becomes a determinate beam. And for this determinate beam, we don't have to find RA to find solution. We can just look at the table. They will give you the solution. That's why you don't have to find RA. Of course, you didn't ask me, so why spend all 30 minutes to find RA? You don't want, right? So the quickest way to find the solution for this one, because now it's a determinate beam, I can just go to look at the table and find the solution there, right? Okay, any of you get a textbook? You can find the solution. Okay, I can again pop it up here. Let's see for everyone to see. All right, let me just pop it up here. All right, so I need to make it a little bigger. Okay, for example, here, for distributed load, immediately you can see the solution there, right? So you can have the Vx, and also you have the delta B from the distributed load. Now, based on what we learned last time, which one would you use for this situation, for this problem? You use the Vx or you use this delta B? Delta B much easier because that's the point you're going to have compatibility equation or the boundary equation, right? So we use this one. Okay, so that's, remember this one? Okay, Q over 8. Okay, so I can write it down here and then I'll switch over. So for this load, you're going to have delta B will be equals to 8 EI QL4. Now let's look at the other 2 loads. Okay, one is a force in the middle. The force in the middle here, right? So what's delta B? Okay, so it's a PA squared, 6 EI, then 3L over minus 8. Okay, let's just copy it here. I'll just copy it here, then we can see it. All right, so you have delta B for the load P will be 6 EI P A squared, then 3L minus 8. All right, now another one we need to find is a force at the end. Okay, this one right here. PL cubic over 3EI. Okay, so QB 3EI PL cubic. All right, so we have this copy down here. So now I can switch back here. You can see. So I copy all the 3 solutions. Now, what's next? How can I use this? Remember, these are the 3 deflections. Actually, it's the delta, not Q, right? It's supposed to be delta. This one. Okay, this will be supposed to be delta. Sorry, it's a bit messy. So all the delta they give you at point B. All right. So from a constant force in the middle, from a constant force at the end, and from a distributed load. Okay. Now, for this situation, what's A? A equals half L. So you just plug in there, right? Okay, so you have 3 solutions. Now, what's the solution for this problem? Add all 3 together, right? So you add all 3 together. That'll give you the solution for this one. Right? It's because individual load, the superposition, principal superposition. The final result of this combined situation supposed to be the solution for each one add together. So I just add all these 3 together. Yes?
The first 2 would be minus?
Okay. Yeah, the question is, should the first 2 be minus, or are they all the same? If you want direction, yes, when you add the 3 together, it's actually, okay, if you look at the table, right? The table gives you a load P is this way. Now you have RB as, you assume it's the other way. So when you add that 3 together, you actually, this will be positive, this is positive, but this one is actually, you should put a negative sign, minus that one. And you should change this P to a minus RB. That's what you do, right? Because there's no P here. This equation they give you over PL cubic over 3EI, but that means the load is there. So in this case, you call it RB, so it's supposed to change to a negative RB. That's it. Yeah.
Let's say for the moments, right? Like the table got moments. Like
Yeah, if they have the table say moment this way, give you this expression. Then now in your situation, if you assume the other way, then it's definitely the opposite direction. All right. Okay, so we have the solution for this problem. That is all 3 added together. Now, how can you make this problem back to the same as this one? Let's call add them together. So this is the delta of the beam. Right? Add 3 together is the delta of the beam. Okay, how can this problem be equivalent to the top one? Or in other words, what's your compatibility in this indeterminate beam? Right. So, because if you look at this point B here, right? When this point move down delta B, then the beam move down delta B. Also, the spring has to compress by delta B. So therefore, you should have delta B of the beam, right, equal to delta of the bar, of the spring. This is the amount of compression. Okay, now delta B of the beam, do we know that? It's here. You just calculate the 3I together, right? Okay, what's the delta bar? How much is the spring going to be compressed? How do you know how to calculate? Or do we know, we learned that already? Chapter 2, right? We have a spring, there is a force, tension, compression. So we know delta bar will equal to what? Will be RB times the length. Let's call the H. That's a spring, length H. Then over EA. Right? Okay. Do we know the E, A, and H? Actually, it seems not the same. What we know is K. What does that mean? That means we know that the delta bar will equal to K times what? What's the K mean? Spring constant. Okay, what that mean? That means force proportional to the deformation. Right? Okay, let me put it this way. Force, what's the force in the spring? It's RB. Right? And what's the deformation of the bar? Spring, that's the delta bar. What's the relation between them? K. That's it. So therefore, what's this one? Supposed to be RB over K. Okay, now can we put this two together, get the solution? All right. Okay, so let's write this final equation, then we can end it there. Okay, what would be the final, the expression you can use? I mean, combine them together, what do you get? Let me see if I can find space here to actually write it. It's hard to find the space. So maybe I'll write at the top here. Write this part. Okay, so the first one will be this term, right? So I'll write the delta B from the load P, all right? Then plus the delta B from the load Q. I mean this expression, right? And then minus the delta B from the load RB. So I mean this expression. Okay, then when you add them together, that's the delta beam. So that equal to the delta bar, right? And delta bar, that's supposed to be RB over K. So that's the final equation. All right? So in this equation, how many unknowns? How many unknowns in this equation? What's unknown? RB. Anything else? That's it. There's only one unknown. So that's a compatibility equation. There's only one unknown. You can solve it. So now again, you can see you don't need to find out RA. You can just directly find out RB. Once you know RB, can you find out the delta B? This how much this point moves? Yes, you can use the quickest way is use this equation. Right? You don't want to go through all these three, calculate, but instead just use this one equation and give you delta B. That's quicker.
Could you find it if you didn't have K?
No, you cannot. If you don't have K, you cannot find it. Right?
If you have to know the link basically for a bar or
Yeah.
cable.
If you don't know K, then you have to know the E, A, and H. Then you can find it. Of course, they can change the question. Okay, so I have this bar here. I want it to move, let's say, only 1 millimeter. What kind of spring suppose I can select? So you select the spring. That could be a design problem. You can change the problem, right? The way you ask it. But the basic equation will remain be this equation. All right. Okay, any questions here? Is this hard enough or easy enough? Yeah.
I thought you only need to use compatibility if you have more than one unknown.
You see your question again?
I thought compatibility was only used because you have more than one unknown in the equation.
Well, we use compatibility because it's indeterminate. You have, in this case, you have 3 unknowns, RA, RB, MA.
Okay,
So,
you have 3 unknowns, not one.
well, this one, the RA, MA part, you don't need to find that out right now because if they don't specifically ask you, you don't need it because solve this problem, I just have one redundant restriction. So I treat that redundant restriction as a reaction force. So I remove it, change it to a force, and find that force. Then the whole problem becomes determinate. I can solve it. Yeah, you don't need that one. Okay. Well, let's do another quick one. I may not go through, but let's quickly do another problem. Say, for example, you have this beam here. All right. Let's say we have 2 restrictions here. A simple beam. All right. So this determinant or indeterminate? Indeterminate. Okay. How many redundant restriction you have here? Or the degree of indeterminacy? It's 2. Because I can remove this one. Let's call this C. This one. And then if I remove this 2, then it becomes determinate, simple beam. Right? So for this one, if I try to solve it, then I have 2 unknown. I have to remove the 2 restriction. So therefore, you will need 2 additional boundary condition or 2 equation for compatibility. Right? Okay, for this one, how can we solve it? We'll just go through the approach, may not necessarily calculate. I don't have a calculator here. Right? So you treat this one, you remove this 2 redundant force, right? And so your problem now become a simple beam with a distributed load and this 2 force that you don't know yet. Right? Now, how can you solve it? You basically treat this, you lucky you have this beam. Okay, you have a RC here, you have a RB here, and then you have a distributed load here. Now, can you solve this problem? Yes, we can find individually. This is equivalent to you have this situation, an RC here, and then you have a RB here, and then you have a distributed load. A distributed load. You have like this 3. All these 3 add together give you that original one. Right? Now, for each of these 3, can you find the solution? Yeah, we can always find it from the table. Okay, now, then how can you make this problem back to here? Or the compatibility? The boundary condition, where the boundary is. You need to look at the point C. For this beam, if you have a random load there, this point C and the point D, they may move a little bit, right? Now, how can this problem back to the same as the top one? You want to make sure their point C, delta at the point C equals 0. Delta at the point D equals 0. Then this problem will back to the original one. So that's the additional boundary condition, or that's the compatibility equation. Right? Okay, so that's the result. All right, so you'll do a follow-up on this one. Okay, I want to move on to a little bit challenger one. We can cover here. Okay, so I want to use a similar problem, but kind of twist a little bit. Okay, let's say I have this beam here, right? So we have a distributed load on top of it. Okay, now this is a cantilever beam. We know it's determinate, right? But I want to actually put a cable here. Basically a spring here. That's like the same as before, right? But this spring, they're not attached to a fixed part. It's actually put to a cylinder. Okay, then attach here. So this cylinder is a kind of long. It's going to another wall. So here is fixed. So this is the wall. Okay, the cylinder, I know the length, all the dimensions. Okay, so it's like I have a cylinder here. This is a cylinder. Then the cable is rolled onto the cylinder, but on the end, hang to the cable, to the beam. All right. So what happens when you apply the load at the beam? The beam tries to deform, moving down. So that pulls the cable. Okay, when you pull the cable is rolled onto this rod or this shaft. So the cable going to pull the shaft. The shaft going to twist. Now we combine chapter 10 with chapter 3. So you have an indeterminate problem with the shaft, cable, actually chapter 2, 3, and 5. So we have all together now. Right? Is this challenging enough?
I didn't make that.
Temperature increase, right? A defect can all be there, right? Okay, let's make it a little bit easier. So drop the temperature change, the defect part. Okay, so we have this cable. So we know the GIP, everything, right? So this beam, we know the EI, everything. Okay, the cable, we know the EA, L as well. Let's call this one H because we use L for the beam. This length will be L. All right, so the question is, when I apply the load Q here, or it can be a load Q plus another load, then how much this point going to move? Again, what's the delta B? This point B here, point A, point B. So what's the delta B will be equal to? Can I give you this in the exam? Well, that's just too many things there, right? But that seems to be okay for homework or for in-class example, all right? Okay, how can we find the delta B? Okay, first, everyone realize how would this system deform? Right? You have the load. Load push the point B part of the beam down. And that is stretch on the cable. So cable will generate some elastic force. And the cable is going to pull the shaft. The shaft will twist a little bit. All right? Actually, another deformation. The shaft, because you pull it, shaft is a bar. Shaft is actually also a beam. It deforms. Right? That's another one. We forgot about that. Shaft is a beam, also deform. Okay, you want to simplify it or just do it this way? Want to simplify it? The easy way to simplify it, just say this point is fixed here. It's rotate but not moving. You can remove that. All right. Okay, if you want, we can just keep it as it is. Don't simplify. Okay, so this basically is another beam, right? So this beam has a E2, I2 as well, because this will deform, bending. Okay, we just need to figure out the compatibility equation. That's it. Other part will be easy. Okay. So let's say this point move delta B, right? What do you have here? For the beam, you're going to have a tension here. Let's call this tension T. Okay. Now this tension T. Okay, so the beam will deform by the load and by this cable. So how much actually the beam deform? Delta beam at the point B from the distributed load. Okay, we had the equation there. I think it was 1/8, right? So 1/8 of QL4, and then 8EI here. That's from the load Q. Now you also have a T tension there, so it will be minus, and that was P become T now. TL cubic 3EI, right? Remember this one? What I'm trying to say is, if you have a beam, okay, you have a load here, P, a cantilever beam, we load P, that's the equation. The reason you have a minus sign, because now the T is going upward. Okay, so that's how much the beam deform. Now, how much the cable deform? Will be T H over EA. All right? Okay. Now, what about the end of this point of the cable? That's going to move, right? One is rotate, second will be bending. Okay, what's the amount of rotation that point is going to move? Should be, okay, let's say this one here. Let's call this one A, B, this point C, right? And then the center, we call it point D. Okay, the point C. how much the point C move delta of the C, the rotation? How much is delta C? You have to use the angle, right? So when you have a shaft, okay, you twist it, you're going to move a distance. How you calculate this? How do you calculate the distance? Should be the radius r times the angle of twist, right? Okay, how do you calculate the angle of twist? R times, should it be T, remember the equation was TL GIP. Okay, what's the T? That's the torque. Okay, what's the torque? It's the moment applied there. What's the moment? Should be R times this tension T. Or this T, that's called T bar, so you don't get confused. This is a T bar, right? Okay, so R times T, that's the moment. And then times L, then GIP.
Is that a T bar up top? I think the cable definition is actually
T. Oh, this one, yes, thank you, good catch. This is supposed to be T there, all right? Okay, so we calculate this one. Now what else? Point D going to move. How much point D going to move? Let's say this length is L2. How much is this point D going to move? You have a load tension T applying here. So if I draw the free body diagram of this shaft, so this is the shaft, you have a T applying here, right? So the shaft is here. That's a GIP. So you have a E2, I2. So how much is this point D? This point D here. How much point D going to move? Okay, so let me put it here. So the delta of the point D will equal to what? A beam with a force at the end. What's the equation? How much this point move? It's supposed to be T L2 cubic over 3 E2 I2. See, we use this equation. Yeah.
For the delta C, is that supposed to be L2 or is that L2?
Okay, question is, this one supposed to be L or L2? L2. Good catch, right? So this is we talk about the shaft. Shaft length is L2. Yeah, all right. Okay, now we write out all the possible deformations. Now what's their relation or the compatibility? They are all a continuous system, right? So they somehow add together should match. Okay, maybe something zero, right? Okay, how are they related?
cable plus angle equals beam.
The definition are both being beat.
Okay, what is equal? I heard a few saying equal there. What we equal? Okay, if you look at this cable, okay, how much the cable get elongated? Is this amount, right? Oh. So this amount, this cable elongated, right? Okay, the elongation of a cable come from where? Come from the point B move. So come from this part. That can make the cable elongate. Also, the point C move, that added to the cable elongation. Also, point D move, that added to the cable elongation. So therefore, all this 1, 2, 3 add together should be equal to the length of the cable change. Right? So that's a compatibility. All right. So let's write down here. So your elongation of the cable, so delta cable, that's this one. So delta cable, suppose equal to, first, from the beam, delta of the beam at the point B, right? And then what else? Then minus how much you rotate. So delta C of the rotation. And then how much this one move? Delta D. Okay, why I put the minus there? Because the beam moving down makes the cable longer. The C and the D movement make the cable shorter. Right? So that's why you have a negative sign there.
So our cylinder is bending.
Yeah, the cylinder is bending, so that makes the cable actually shrink. That rotation makes the cable shrink. So, but the beam moving down makes the cable longer. So that's why you have this equation. So that's your compatibility equation.
How do you solve the change in beam if that's more circular?
Well, once you have the equation, you can solve for it. Right? You plug everything in here. This is your compatibility equation.
Yeah.
So you can solve it.
Is everything added?
Yes.
Can you explain why the elongation of point C, the rotation is negative?
Okay, because the cable is pulling here. Not pulling makes the shaft rotate. So the shaft rotate follows the same way. So when the shaft rotates the phi, this point C is going to move down a little bit. And that makes the cable shrink. So that's why it's a negative contribution. All right?
I don't know if it helps. To me, it just makes more sense to say beam is just going to be the sum of everything else. It just kind of puts in a better perspective.
You heard that?
Everything has
How much the beam, this point C moves, equal to how much the cable elongates, plus how C moves, how D moves. Does that make sense? Yes, that's another way of looking at it. So you're absolutely correct. It's just the deformation relation. You can say, okay, how much point B moves? It's all of them add together. That's fine. Right? Okay, any questions here? Very good. Okay, now when you go home, practice on the homework. See if it's harder than this one or easier than this one. All right? But always the idea is the same. You use the compatibility and link them together.